This is only a test.
Welcome to This Is Only a Test, where we discuss interesting stories in diagnostics. I'm your host, Mickey Urdea from Halteris Associates. We had a recent episode on proteomics, and I mentioned during that presentation that I would come back with another episode on algorithms. And specifically, algorithms are the algebraic expressions used to combine different markers into one test and to provide better results by doing so. Sometimes those tests will require just biomarkers like proteins or RNA or something like that. Sometimes they'll also include clinical information or patient attributes, and I'll talk about the pros and cons of that a bit here as well. So the intent is to improve the clinical performance of a test by doing this combination, to provide additional sensitivity and or specificity. And oftentimes it really does help with specificity in particular. But sometimes it works and sometimes it doesn't. Also, there are times when we tend to fool ourselves into thinking that it works, and I'm going to discuss that and why that's an issue. But I got to say, I think it's a bigger problem now than it was even 10 years ago. And I've confirmed that with a number of biostat friends, and they think that's the case as well, and I'll explain why. Also, the last time I presented with the proteomics, I talked about it, the startup company Tethys Biosciences, which I had founded, more than a decade ago. And the reason I brought it up is the lessons learned there on how to develop proteomic-based platforms. But now I'm going to talk about it in terms of using the experience that I had in developing these multi-analyte algorithms. This is not meant to be an attempt to educate you about how exactly to derive, calculate the algebraic algorithm, which, by the way, both the word algebra and algorithm come from one particular man. It was a Persian polymath, Muhammad ibn Musa al-Khwarizmi, who lived in Baghdad in what they called the House of Wisdom. Just amazing that one person contributed that much, but the guy contributed a lot more as well. Anyhow, what I'd like to do is describe today how the algorithms are developed, how to optimize them, best practices in developing them, potential to overestimate the performance, and some practical issues in implementing these kinds of algorithms and use in clinical diagnostics. But first, I want to describe some of the major tools that are used in this sort of development. You may have heard of ROC curves before. ROC curves are defined as receiver operating characteristic curves. It's a graphical representation of the performance of what is referred to as a binary classifier at different classification thresholds. More specifically in diagnostics, it is a plot of true positive versus false positive results, the Y versus the X axis. And it's a very powerful tool. So what's typically done with these ROC curves is to actually determine the area under the curve. That's a very useful parameter. And I'm going to talk about how to think about that in a few moments. But that's the idea. You're calculating the area under the curve. So to generate one of these AUCs within a ROC curve, there are typical sort of approaches people have taken. Lots of cases in literature of how to calculate these things. Usually the algorithm is based on a combination of quantitative results for a biomarker, for instance. For instance, if it's a protein, maybe it's picograms per mil. If it's RNA, it might be the number of copies of the RNA in the sample. That can also be supplemented with additional information, such as patient attributes, such as BMI, such as perhaps your year of age, maybe even the sex. So these attributes can be used in a numeric way as well, something like a BMI, get a number for that, or might use simply it is or it isn't that, for instance, sex. And that can be quite interesting, actually. Some of the work we did at Tethys years ago on primary AMI risk determination involved a different set of markers for smokers versus non-smokers, which was a big surprise. But we did have to do it that way. Another recent case I'm aware of is a company that I saw recently that's looking at early detection of cancer. And they actually found that they need to use a completely separate set of proteins in males versus females. I've not seen that before, but you have to be aware that that could be the case. So these algorithms oftentimes have weighting factors for specific contributors. You might find that protein 1 actually should be weighted 2 times as much as protein 2 because that actually improves the AUC. The AUC is measured between 0 and 1, and I'll show you what that means in a few moments here. The y-axis of the rock curve is sensitivity, true positive rate, same thing. And then whereas the x-axis is 1 minus specificity because we're not looking at absolute specificity, but the false positive rate. And that gives us that. Best practices involve actually using two different sets of samples when you're trying to develop and validate the algorithm. So the first set is usually referred to as a training set. There are all kinds of statistical tricks to try to increase the likelihood of that being a useful algorithm when you get done with it. For instance, what they refer to as cross correlation, where you take different portions of the total number of samples and you test it on that. Then you move to another set, and then you randomize and do it again, sometimes for quite a large number of different yeah, calculations. But there can be what's referred to by statisticians as overfitting of the model, where the algorithm is specific to just that data set. And if it's not generalizable, and when you try another data set, it simply doesn't work as well. Now, the way you can determine that is by in fact having a separate set of samples that you test to validate that initial algorithm. Train it, then test it and validate it. There are two different ways people do this. One is to actually take the sample set that they've got, maybe take a portion of the samples out of that, save that to do validation later. The other one is, which I prefer, is to actually have a completely separate set of samples, even the different clinical study, and validate your algorithm on that. And I'll come back to examples where people do different things and why that can be a problem. You might find that when you try to take that algorithm and apply it to another set of samples, that it just doesn't work well, in which case you're going to have to go back and either come up with a different algorithm with what you've got, add new biomarkers, or it just may be that these biomarkers are not going to give you the kind of performance that you require. So it's time to rethink. When you look at these rock curves and you're looking for what the AUC is, what does that mean? What does the value of the AUC mean to you? Well, in a perfect situation, what you get is the entire inside of the graph is the AUC. You're hoping that you're going to get a perfect AUC, which would be 1.0. 1.0 would mean that your sensitivity is at its highest point, as well as you have the lowest point for false positive rate. So that's going to be up in the upper left-hand side of the graph. Random results are actually going to be where you've got a line straight diagonal right in the middle of the graph. That means that you've got a zero point 0.5 AUC, basically 50%, which means it's a coin toss. So you're typically looking for something that's going to be somewhere in between. And when you look at these curves, you often will see that they are fairly, curved, but I'll show you examples where they've got odd kind of shapes. But you actually have a choice as you're determining what your performance is based on what you're going to do with the test. So, for instance, there may be situations where you're doing screening. And with screening, you want very high sensitivity, and there's probably going to be some acceptable false positive rate, which could be fairly high depending on what the application is. In contrast to a situation where you're trying to diagnose and you're very concerned about false positive rates in that particular case, so you'll slide to a different place on the curve to get acceptable sensitivity and very high specificity. So, it just depends on the particular type of test you're trying to develop, and you'll have choices. So, when you look at these curves, they typically are curves, and you have different options of where you actually set the true positive versus the false positive rate. You can determine that by moving a different place on the curve. So let's say what I want is something that's very sensitive with some acceptable specificity or false positive rate. I might maximize for the sensitivity and look at what that means in terms of the false positive rate and ask myself, is that an acceptable performance? Would, let's say, a 20% false positive rate be acceptable if I can get 80% sensitivity? Sometimes it is. But there might be other situations where you really don't want to have a problem with specificity. So you set the curve, look at a curve, a spot on the curve where the false positive rate is very low with an acceptable sensitivity. So depending on what you're doing and what the acceptable performance is, you have choices on the curve. So the challenge as a developer of tests, and you want to use these multi-marker approaches, is trying to come up with an AUC, which is above random as far as you can get. I've never seen anybody get perfect, but there's value to increasing the AUC, and that's the challenge, increasing the AUC. Now there are a bunch of other aspects of developing these curves that I'm not going to go into, but if you're interested, there are a lot of works out there where you can look at the different types of rock curves. There are empirical or non-parametric methods. There are binomial parametric versions of these curves. I'm not getting into that right now, but just recognize that that is the case. There are actually different forms of these rock curves. They are, for instance, what are referred to as empirical or non-parametric versions of them. Then there are bimodal uh, parametric versions. I'm not going to get into that today, but it's something that if you really want to dig deeply into how these things are used, you might want to look into yourself. So, just general rule of thumb in terms of the how good your AUC is. If it's somewhere between zero point 0.5 and zero point 0.6, it's usually considered a fail. It just the performance isn't good enough to be implemented as a test. If you're somewhere between zero point 0.6 and zero point 0.7, that's considered poor, but you might find situations where it's acceptable. Between zero point 0.7 and zero point 0.8 is fair, and I've seen situations where that is going to be acceptable. Um, and then zero point 0.8 to zero point 0.9 is actually quite good. That's hard to do. In fact, my experience is every zero point 0.1 you go up is almost like an order of magnitude more difficult than the previous. But, if you can get to zero point 0.8 to zero point 0.9, that's usually very good. But above zero point 0.9 is excellent, really quite good. So just rule of thumb. So I'm going to take a look at a couple of examples of the development of rock curves and AUCs using multi-marker approaches and just make some comments about it. So the first has to do with an algorithm that was used for looking at hepatocellular carcinoma. And the authors actually presented a very nice graph, very nice figure about how the original work was done that they're basing their new work on. And I'll come to that in a few moments. But this previous work had to do with looking at 41 different known biomarkers and trying to pare it down into as few markers as possible to get the performance they required. And they were looking at this in early stage HCC, late stage HCC, comparing it to a control panel. So people that didn't have HCC at all. There were two algorithms that they wanted to look at that were developed by this group. One is called GAD, the other one's called GLAD. So in this particular study that was done previously, there were 1,056 samples that were split into the early, late, and controlled samples. Three-quarters of the samples were used to do the training set. So they did what I was mentioning before, this cross-correlation study, where they are using a logistic regression approach, and they did 200 different calculations with that cross-validation. They then determined what the coefficients were for their algorithm. They determined the sensitivity specificity, and then they did another cohort, which is the one quarter of the original cohort left. And then they did more than I would have done. I mean, they actually did cross correlation on it again. As far as I can tell, they actually modified the algorithm from the first training set. So I think in terms of this being a second training set, maybe I'm wrong, but that's what I would refer to that as. I did not see them actually test a completely separate panel from the original study, but the new authors did do that. That process worries me because it can lead to this so-called overfitting. It may be that the first algorithm didn't work that well, but they got a better algorithm when they did the second set, but now they haven't tested it on a new cohort. That just, I don't know. I find that very difficult to swallow. And there are many publications today, and this is one of the things I was mentioning earlier that concern me about what people do today versus the past. There are a lot of publications out there where they only do the training set. They actually don't do a validation set at all. They present just that algorithm and just that AUC within a rock curve. And I mean, I've seen this break down so often. And in many of those publications, they get very high AUCs, high 0.95, 0.98. I will bet you that if they did a true validation study, it would not hold up. That's my opinion from my experience. Um, so, just as an example, we went very far at Tethys to make sure that we got a good validation. We did the training set on a completely separate cohort, completely separate study. We were looking at the risk of developing type 2 diabetes. So we developed that algorithm. We froze it, and then we did another set of samples that had never been touched, ran it on that, um, and we actually sent the data to a biostatistician at Stanford named Mike Walker and had him do the analysis on it to determine what the AUC was. And fortunately, the AUC for the second set was zero point 0.1 higher than the first set, which delighted us. So I think that's a level of rigor that most people haven't done but should do. So let's take a look at what the authors that wanted to compare this GAD and GLAD algorithms were looking for. So from the previous work there had been a couple of very specific biomarkers that were shown in this GAD algorithm, and they were AFP and DCP. And then this GLAD algorithm added one new marker to it, AFP L3. So it's a different form of AFP. And they also included the gender and the age in this algorithm. All right. So the early reports had suggested that the addition of the AFP L3 improved the performance relative to not having it in the GAD algorithm. So let's take a look at this. What do they do? Um, they have these rock curves here. There are a number of different types of curves. They have it for both the early stage HCC and all stages. And what they looked at was the specific contribution of AFP-L3 itself. That's the yellow line. Note that it's kind of flat. In fact, it's not very good at all. It's almost random. So that's a concern. But now they took a look at what happens if you add the other two markers, AFP and DCP. Those are the blue and the orange curves there. Neither of them alone contributes sufficiently to it. But now you combine them together and you get the dark bluish curve that is the so-called GAD. Now, if you add the new marker, AFP L3 to it, that curve looks just like the one with the previous GAD that didn't have AFP L3. Conclusion, AFP L3 doesn't add anything. But note what's going on here, which is you're looking at how to build content to get up to the performance you want by adding new markers that improve the AUC, and that they could tell that neither AFP alone or DCP were going to be sufficient. All right, so I'm going to talk a bit more about that because that's the trick. That's what you're trying to do. You're trying to increase the likelihood of performance being improved by increasing markers. So take a look at another study that was done and reported recently on ovarian cancer biomarkers. And they had been looking at a number of different markers and looking at what their specific contribution to the AUC was in a rock curve. So this is one at a time now, each marker. So you see that they've got the AUC of these markers, and then they've ranked them in terms of which contributed the greatest portion of the AUC. So you see that CA125, that grand old Centocor marker, had the best contribution of 0.896, which is pretty darn good itself. What they were looking for was improvement to that. So you see that there are other markers like number 3, CA72-4, number 2, CHE4. Those are the individual contributions. But the question is, if you combine them, do they contribute new information? Oftentimes you find that they don't, or they contribute much less than you expect. So let's take a look at that. So these authors also took a look at besides just the single markers, and they're showing the single markers uh, in the red. So different markers that have different contributions of AUC, and there's that CA 125 to the far right. Um, and then they looked at two markers at a time. So when they did that in the blue, you see that now they're building from that CA 125 alone, trying to see higher AUC content. So you see if you add HE4 to CA 125, that looks pretty darn good. And if you add, for instance, prolactin to it, you get an even bigger bump in the AUC. But now the question is, if you start putting them together even in larger numbers, do you improve it even more than that? So this can get kind of complicated. I'm showing in the next graph or the next table here from them, where they're looking at the three best contributing markers up there, and then along the top, and then on the left-hand side, you see other markers from that list and what they contribute. And if you just take a look at the delta AUC for each of those, you see that some of them contribute more than others when they're combined. So, for instance, adding prolactin to CA125 in bold there, 0.0011, that's the contribution that it adds to CA125, despite the fact that prolactin alone is almost zero point 0.6 and CA125 is almost zero point 0.9, you don't get as much of a contribution as you might expect. So that's why it takes a while to try to put all these things together and see what you can uh, piece together and what the performance might be. I'm going to be showing a number of tables and graphs and figures here, and all those will be available in the show notes for this episode. So I showed a fairly simple example here of combining, let's say, just two markers and what they contribute. But what really happens is you start looking at many different combinations. And this can be kind of difficult to work with. Um, Often, though, you find that the largest contribution is from a small number of markers. For instance, in the case of proteins, my experience is like 2 to 4 markers contribute most of the AUC you're going to get by adding new markers to it. Um, there are probably exceptions to that, but that's been my experience. And when you start adding more beyond that, you're going to get a lot less increase in performance. Usually less than zero point 0.1 AUC for sure. And you may need 3 or 4 additional ones to get to that additional contribution of zero point 0.1. Also, what I've typically found is that as you start adding these things beyond the core group that contributes most of the AUC, you start finding that you have the ability to take one of those proteins out and add another one, which contributes just as much as it did. That is, you have choices within the algorithm as to which proteins to use. So that can be tricky, not only from a development point of view, but also to write patent claims. You have to start thinking about combinations. And at Tethys, we spent a lot of time on that. Finally got that type of patent through the examining office, but and issued. But it's not easy to do. Also, I have experience in doing this with multiomics approaches. Again, at Tethys, we were using proteins, but we were collaborating with a company in Davis called Lipomics. We ended up buying them, as a matter of fact, because we got very excited about the contribution of the lipids to our algorithm. And we spent quite a bit of time working with them on that and finally came to realize that the lipids really weren't adding biological information beyond the proteins. And we could replace every lipid with a protein. So we ended up going with proteins only. It's less expensive, less labor in terms of processing samples. But I was surprised when we found that that could be done. We could completely replace one type of biomolecule with another to get the same result. Another thing that I would consider here is the use of that additional information from patients' attributes or from clinical data, because you got to ask you the question, where is that going to come from when someone runs your test? Are they going to simply be able to talk to the patient? They know something about them that they can add at that time, or is it something you have to look at that's an electronic medical record? in which case that means you have to have connectivity to that, which also means that's going to be rather limiting, and the laboratories are going to want to use this test. Something else that I think that needs to be considered is also the absolute number of markers. People tend to want to add as many markers as they can to keep increasing the AUC, but with some types of assays, you have to be worried about what the CV is for the assay. So you can get to a point where you add more markers. Now you've increased the error in such a way that you get a poorer performance when you take that in consideration, not a better performance. And my experience has been, at least with standard immunoassays, you get to that point at about 6 or 7 markers. Uh, there are better methodologies coming along that might improve that AUC, as well as giving you sufficient reproducibility that you don't have to worry about that. But you got to take it into consideration in terms of both the number you add and then what the platform is you're going to use to deliver that result eventually to the marketplace. So I've tried to describe to you how these algorithms are developed using ROC curves and AUC, how to optimize them using different combinations of biomarkers and looking at the AUC contribution, the best practices in terms of the types of studies you do, in terms of training sets and validation sets, uh, the potential to overestimate the performance of the assay based on that kind of approach, and some practical issues in implementing these things into clinical practice, such as the total number of markers, the platforms that you need to use, and then reproducibility issues. So I hope you find this useful, and thank you for joining us for this episode of This Is Only a Test. This is Mickey Urde for Altaris Associates. Bye.